Today we're looking at lesson 5.8, more or less. And today's objective is, given a system of linear inequalities, I can graph the solution set in 2 out of 2 problems. So in the last lesson, we looked a little bit at linear inequalities, and we're going to expand on that a little bit more today. So back to good old Carlos and Clarita and their pet sitting business. Previously, we looked at both the cost constraint and the space constraint to find combinations of cats and dogs that would work for their business. So we said they had cost constraints based on cages they were going to buy. That's this orange region right here. And those were combinations of cats and dogs that would work for the number of cages they could buy. And then we also talked about the space constraints for the shed where they're going to house the cats and dogs. And that was this blue region here. And these are the corresponding inequalities we came up for both of those. And you can see this region right here where they overlap, that was the area where we said both the space and the cost constraints would work. So all of these inside, all these combinations inside this double shaded area are options for their business. But they also want to make sure their business is making enough money, right? That's a very common constraint we'll put on a business. Make sure that they're making enough money to make it worth their time and make it worth their costs. So let's take a look at what their profit constraint is. So after a few options, they tried a few different things, the twins have decided that the best rates they can charge are $6 per cat per day and $15 per dog per day, which honestly is pretty good rates. Their neighbors are getting a steal on pet sitting. In order to recoup their costs and invest in their savings account, they want to make sure they're making at least $150 per day. There's that at least phrase. Indicates to us we're going to be looking at an inequality. So what are some numbers you notice in this problem? What are some numbers you can see? Let's see, I think we have $6 per cat per day. We also have $15 per dog per day. And $150 that is at least what we're making for their business per day. So how do we put this together? Let's see, we said cats were going to be our X variable, the number of cats they have, and dogs were going to be our Y variable, the number of dogs they have. So how much money are they bringing in cats? If they have X cats and they have $6 per cat per day, the amount they bring in for cats should be 6 times X. That's how much they will make on cats every day. Similarly, for dogs, it's going to be the Y variable, and they're making $15 per dog per day, so it will be 15Y, 6x plus 15y, and we're going to be comparing that to 150. And we have to figure out which direction is our inequality going to go. Is this side bigger or is this side bigger? Well, it says at least $150. So that tells us $150 is the least side, the smallest side. Alligator does not eat the small side. So the money we make in the business every day has to be bigger than 150, or it could equal 150, so we're going to put an equal sign in there too. All right, so that sets up our inequality in standard form. And let's go through the steps now of graphing a linear inequality so we can come up with our solution set. Our first step is to solve for y. Now, if you'll remember why we want to solve for y, that's because we want to graph this in slope-intercept form. That helps us figure out which side to shade. So I'm going to circle my y variable, highlight my other terms on the same side, and we're going to solve for y. Let's see, let me draw my line straight down here. We'll get rid of the term that's furthest away from y, so we're going to subtract 6x from both sides. These 6x's cancel, and we have 15y. We don't flip the sign because we don't flip it for subtraction. On the right side, we have negative 6x plus 150. Remember, I like to write that x term first so that I get it into our normal mx plus b format, so I just write the x term first. And then our last step to get y by itself, we're going to divide both sides by 15. On the left side, we're left with y. We divide it by a positive number, so we don't flip the sign. And now I'm going to split this out into two terms. Take the denominator with me. So we have negative 6x over 15. And then we also have 150 over 15. If we simplify each of these separately, we will get, let's see, negative 6 over 15. So both of those are divisible by 3. We get negative 2 on top and 5 on the bottom. So negative 2/5 x. And then 150 divided by 15 is going to be 10. So there is our inequality in slope-intercept form. Right there, negative 2/5 x plus 10. We solve for y. Okay, our next step is to plot 2 points. So we have our y-intercept is 10. Y-intercept is 10, and our slope is negative 2/5. So we're going to start at that y-intercept and plot that point on the y-axis right here at 10. And then we'll take our slope and go down 2 and right 5. So we'll go down 1, 2, and before I go right 5, just notice here that this scale is a little bit different. Each of these lines is 2, 4, 6, 8, 10. So we went down 2. We're going to go over 2, 4, 5. So just being careful with that scale. All right, we plotted 2 points. And that's step number 2 done. Number 3, we ask, is this a dotted line or a solid line? How do we tell? Well, we have to look at our inequality symbol and say, does it have an equal sign on it? If it does, then it's a solid line. If it doesn't, then it's a dotted line. We do have an inequality, we do have an equality here, so it's going to be a solid line. We'll draw a line like that. So step number 3 is done, and our last part here is to shade the side that contains our solutions. So in this case, we have y on the big side of the alligator. See how the alligator's eating the y? So the big side tells us we're going to go above the line. So we'll shade everything above the line. And I'd fill this in, but I'm not going to be particular about it right now. So this whole region contains our solutions for our profit constraints. Let's talk about what that means real quick. So we said they want to make at least $150 per day. So any of these combinations of cats and dogs, for instance, 30 cats and 10 dogs, that's in our shaded region, that would allow them to make at least $150 each day. That's true for any point inside the shaded region. Here, anything even on the line would work, but these points down here would not make enough money to satisfy their profit constraint. All right, so here are the 3 constraints we've identified so far. We have the cost constraint on the cages in the orange region, the space constraint on the blue region, and the profit constraint here, the new one we just did, in the green region. How might we combine all of these together to figure out what combinations would work for everything? So within their costs, within their budget, within their space constraints, and making enough money to make their business worth it. How can we figure that out for all of those constraints? Well, we can graph all three at the same time. Look at that. We just graph them on top of each other. Now you'll notice it can get a little bit tricky, a little bit complicated, because now this entire graph is shaded. We have to pay attention to what direction everything is going. So remember, our cost constraint was this orange one, and it went down. Our blue one was our space constraint. That one also went down. And then our green one was our profit constraint, which went up. So the region that's bounded by all three of these constraints is this right here, this sort of path right through the middle of it. These are the points, these are the combinations of cats and dogs that would work for all three constraints, cost, space, and profit. Only these ones in here would work. So let's try to find three specific combinations that would work for all three of these constraints. Notice we can write this as a system of inequalities with three constraints now, three different inequalities. And we're just looking for any 3 points inside this region. So I'm just going to choose maybe this point right here. This one looks good, 10, 10. That's a possibility. And maybe, let's see, how about 20 and 8? That one might be good. And let's do 30 and 2. That's right inside. What about this one? This one's 15 dogs, 0 cats and 15 dogs. Can we do that one? Would this one work? So this one is on a dotted line. It's right on the dotted line boundary. And since we don't include dotted lines, that one actually doesn't work. So we couldn't do 15 dogs and 0 cats. We could, however, do 0 dogs and 40 cats. That's a solid line and is otherwise inside our other boundaries. So we could do 40 cats and 0 dogs. That's another option. We found 4 combinations. And maybe let's, just for good measure, let's do one more. Let's do 2, 4, 6, and 12. 6 cats and 12 dogs is in our region. So now that we've found some combinations that will work for all of our constraints, let's try to figure out which one will make the most money, right? That's what we were concerned with today, is their profitability. So let me write down those points we came up with. 10, 10, 28, 30, 2, 40, 0, and 6, 12 were the points we came up with. And we're going to try to figure out which one will make the most money, which combination will make the most money, so it's the best option for them. So here we have 10 cats and 10 dogs, so we'll have 10 cats times $6 per day, plus 10 dogs times $15 per day. That equals 60 plus 150, which is $210. We do the same pattern here, 20 times 6, 20 cats times $6 per day, plus 8 dogs times $15 per day. 20 times 6 is 120. And 8 times 15, I think that's actually also 120. 120 plus 120 is 240. All right, 30 and 2. 30 cats, 2 dogs. That'll be 180 plus 30, which is 210. 40 and 0. 40 cats plus 0 dogs is going to be 240 plus 0. And our last option was 6 and 12. So 6 cats and 12 dogs will be 36, and 12 times 15, let me do that in my calculator, 180. And that looks like 216. So which of these options are the best for their mix of cats and dogs? Looks like that one is 240 and that one is also 240. So those have the same profitability. So either 20 cats and 8 dogs or 40 cats and 0 dogs. Either of those would be good options. 20 cats and 8 dogs or 40 cats and 0 dogs. So we could recommend either one of those. We might consider other things like how many neighbors have cats, how many neighbors have dogs. Maybe we don't want to limit to only cats. Maybe we'd recommend this one just to have a few dog positions available, a few dog cages available in case they're needed. So a quick summary of what we figured out on that last slide, or in that last scenario, is that when we have systems of inequalities, sometimes we have more than one, we are looking for the region where they all overlap. So you can see here we only have 2, and where they overlap is right here, this darker shaded region. Over here we have 3 inequalities, so we kind of have to pay attention to what is shaded where. You can see on this blue region we're shading above the line, above the line, above the line, above the line. This red region we're shading below the line, so below, below, below here. And in this orange region we are again shading below the line. You can see the orange shading is down from the line, down here. So if you look at all 3 of these lines, you can see the region that's completely overlapping is this one right here. So any of these points inside this region would satisfy all 3 of these conditions, all 3 of these inequalities. Now sometimes systems have no solutions. And there are several ways this can happen. Here's an example up here where you can see we have 3 systems we have 3 inequalities in this system. And we have an overlap of 2 here, an overlap of 2 here, and an overlap of 2 here. But this one's going to keep going up, this one's going to go to the left, and this one's going to go down to the right. None of these will ever cross. None of these will ever cross their line, so they're just going to get further and further apart. Since we don't have any region where all 3 overlap, right, these were only 2, 2, and 2, that means we'd have no solutions here. This one's a little bit different, but again has no solutions. You'll notice 2 of these lines are parallel. This is a good indicator that something interesting is happening and you might not have any solutions if you have parallel lines, although you might. We have to figure out where our overlap is. So in this one you can see we have an overlap of 2 here, an overlap of 2 here. This one's going to go up, this one's going to go to the right, and you can see they're never going to cross because these 2 lines are parallel. We also know that because their slopes are the same. Whenever we see the same slope, we know we have parallel lines. So these lines are never going to cross. That means these regions will never join, and we will never get a place where all 3 conditions are satisfied. This is, again, no solutions. So let's practice with a few inequality systems problems. Okay, this one says, which points satisfy the system? Select all that apply. We have a system of 3 inequalities and then a bunch of points we need to check. So where would you start this one? What do you think we should do? We have a couple of options. We could use Desmos to graph, or we could plug in these points into each one of these and see if they worked for all of them. Now, I like the Desmos option on this because plugging these in, like plugging 8 points into 3 equations or 3 inequalities, would take a very long time, whereas Desmos is going to be a lot faster. So let's give this a try in Desmos. Let's pull up Desmos, type in these equations and even these points, and it'll tell us which ones are in the overlapping region. So here we are in Desmos, and I'm just going to type in these equations. We have y is less than or equal to. Now notice how I type this. I type a less than, and then I type the equal sign, and we'll actually just automatically do that less than or equal. It's really handy that way. And then I just type in 2x minus 3. That was our first inequality. Our second one is y is less than 1/4. Once again, how we type this is just 1, and then the slash, which will give us a fraction, and then 4 on the bottom. Now I type the right arrow key to get out of that fraction, and then I just type the rest, x plus 4. There is our second inequality of this system. And our third inequality, let's move my mouse out of the way, y is less than -2. So there are our 3 options, or our 3 inequalities. We're going below this line, and below this line. So all of these must be less than. It's less than, less than, less than. We're going below the line. So this region down here is where we're overlapping all 3, the blue, the red, and the green, this region. And we're going to just keep plotting the points that they gave us and see which ones are in that region. We can even do this in Desmos. So I'm just going to press enter so I get a new line. And I'm going to type in our first point, which is 5, 0. I can even click label here and it will label it so I know that one is 5, 0. Now I can see this one's in the blue and red overlap, but it's not in the green overlap. So this one's a no. That one doesn't work. So I'm going to type in our next point, 2, -4. Now this one is in that overlapping region. It's below the red, it's below the blue, and it's below the green. So this one does work. 2, -4 is going to be one of our values. I'm just going to go back here and mark that. And then our next point is 0, 0. That one's only in the blue. It doesn't satisfy the red or the green. So let's type in our next one, 0, 10. Oh, well that one's off the graph. I can't see that one. So I'm actually going to zoom out and see if I can see that point now. 0, 10 is up there. That one satisfies none of our inequalities. That one's like the nopest of the nope. Definitely doesn't work. Okay, let's type in our next one. 0, -10. That one's a little bit hard to see because they made it green. We could actually change the color if we want. I'm going to change that to black so we can see it. 0, -10 is down here. It's below all 3 of these lines. So yes, 0, -10 works. Let's mark that one. 0, -10. Okay, we have 3 more to go. How about 7, -2? Where is that one? Okay, that's over here. Looks like it is below the red line. It is below the blue line, but it's right on that green dotted line. What does that mean? Do we include it if it's on a dotted line? No, we sure don't. We don't include the points on the dotted line, so that one doesn't work. It's very close, but it doesn't work. Our next one is 5, -5. Let's put a label on that one. That's right here. That one is in the region. So we'll mark that one. Yep, that's a 5, -5 works. And our last one is -3, -3. Let's label that. Okay, so that one's right here. Looks like that's in the green and the blue region. but it doesn't fall below the red region, so that one doesn't work. So we've checked all of these points now. These three were the only ones that fell in that region, the completely overlapping region. Let's try another one. So now we need to indicate which side is shaded for each boundary line. So that's nice of them to graph our lines for us already. Now we just need to figure out which side to shade. It says shade the overlap to show the solution to the system. Okay, so I think we're going to need to figure out which line is which. How might we do that? Maybe we can label these like A, B, and C. We'll figure out which line is which over here. So there are a couple ways we could do this, but I'd like to look at our y-intercept. Since all three of these y-intercepts are different, they're going to make these lines distinct. So if I go find the y-intercept of 5 right here, that line must be line A. So I'm just going to label this as A. Similarly, B is going to be at -3 y-intercept, so -1, 2, 3. This line must be B. And that means our final line must be C, y-intercept of 3. 1, 2, 3. Yeah, this one is C. And now we just need to figure out which side we shade for each of them. So remember, we're going to shade the y value in each of these. And we need to ask, is the alligator eating the y side or the other side? In this case, the alligator is eating the other side. This side is bigger, so this side is smaller. So since the y is smaller, we're going to shade below the line. We're going to shade below the A line. So I'm just going to draw my little arrows, tell me I'm going to shade below this line. Now let's look at B. Alligator's eating the y side, so that tells us we're going to shade above the B line. So this is our B line, we're going to shade above it. And our last criteria is our C line. Y is again on the smaller side. So this is going to be below the C line. Here's our C, so we're going to do down arrows on the C. And we ask, which region, which section of this graph satisfies all of those constraints? Well, we have down arrows, left arrows, and up arrows here. It looks like it's that triangle right in the middle. This is our region of solutions to this entire system. All right, one more problem for practice here. They want us to write the system of inequalities that matches the shaded area. Okay, so this is kind of the reverse of what we just did. We're looking for the equations, or the inequalities rather. We're looking for the inequalities, and then we need to figure out which side we shade. So let's again just label these A, B, and C. Those are the lines. We need to figure out what the equation of each line is. Now we can use good old y equals mx plus b. We just need to know our y-intercept and our slope. So let's look at A. Our y-intercept here is -1, 2, 3, -3. And our slope, let's see, I have another point right here. I could go up 1 and write 1, 2, 3, 4, 5. So that's a rise of 1 and a run of 5. So if we were to write this as a line, right, the equation of that line would be y equals mx plus b. We could write -3, we could write add -3, either would work. Now that's just the equation for the line though. We need to ask, is this going to be less than or greater than? Are we shading above the line or below this line? Well, we're shading over here, so this looks like it's above the line. So our y is bigger. We're going above, so the y is bigger. Alligator eats the bigger side. And then we do keep that inequality symbol because this is a solid line. Okay, so we need to do this 2 more times with lines B and C. We're looking for a y-intercept and a slope. Our y-intercept is 5. And our slope, let's see, I have another point here, so I could go down 1, 2, right 1. So down 2, right 1. That's going to be a slope of -2. Our equation for this line then will be y equals -2x, right, our mx, plus b. And then we need to figure out which side we're shading. We're shading this side, so that looks like it's above the line. So once again, this is going to be y is bigger than, because that's the side we're shading, alligator eats the bigger one. This is a solid line, so we keep that equal sign. Last one, C. Let's find our y-intercept. Looks like that's -7. And then our slope is, let's see, here's another point. So we go up 1, 2, 3, and right 1. So a rise of 3, a run of 1, our slope is 3. We get y equals 3x minus 7. And our last step is to figure out what side we're shading. So let's see, we're shading this side of the C line. That's below the line. So that means y is going to be the smaller side on this one. Alligator eats the other side. And finally, we do keep that equal sign. This is also a solid line. So those 3 together are our system of inequalities on this one. So that wraps up today's objective. Given a system of linear inequalities, I can graph the solution set in 2 out of 2 problems.